Before we go to maladaptation, let me revisit this issue of comparing different greenhouse gases. I mentioned that CO2 equivalent is something that we have done all along. We have used that unit many times. So if you look at the global mean radiative forcing since 1750, there are well-mixed greenhouse gases, short-lived greenhouse gases, short-lived gases and aerosols, other forcings resulting in a total radiative forcing of over 2.29 watts per meter squared with a range of 1.13 to 3.33, and the level of understanding is not the same for all of them. So CO2 we know very well. Solar radiance changes. The solar modeling is pretty good now, but the confidence there is medium. Its forcing in general is relatively tiny, and it has flattened out in the latter part of the 20th century, so doesn't have any significant contribution at all to the observed warming. CO2 obviously dominates with 1.68 watts per meter squared with very high confidence. Methane, not as long-lived, but very much higher greenhouse warming potential of 25 compared to CO2 over 100 years, has more than half of CO2 forcing, and we have high confidence in it. Halocarbons, a little contribution. N2O, small but increasing. Carbon monoxide, non-methane volatile organic compounds, and NOx, and so on. So is this the best way to compare different greenhouse gases when it comes to Earth system feedbacks and climate change? The argument is that not necessarily. So I'm going to just show this figure from a paper listed here, which looks at global warming potentials and also global cost potential, cost-effective temperature potential, and global temperature change potential. In other words, instead of just relying on the tables we used before of computing CO2 equivalent by using the global warming potential of different greenhouse gases and converting them into CO2 equivalent, if we instead focused on global cost potential and the cost-effective temperature potential and global temperature change potential, you will see that the relative valuation of methane with respect to CO2 would be very different. So the global cost potential and cost-effective temperature potentials are pretty close to each other, but the global temperature change potential is much higher. So the main point I would leave you with is that comparing different greenhouse gases is not as straightforward as when we just use global warming potential, because, for example, methane doesn't have a direct impact on vegetation, but CO2 does. So, but ozone does as well, and so on. So we have to consider non-climate impact or indirect impacts as well. So another thing to keep in mind along with everything we have been looking at. So we've been talking about adaptation and the need for reliable information at the local levels for good, solid policies for adaptation and strategies and implementation. There is also the question of maladaptation, which is defined as action taken ostensibly to avoid or reduce vulnerability to climate change that impacts adversely on or increases the vulnerability of other systems, sectors, or social groups. Okay, so this is here showing maladaptations are poor choices among alternatives, choices that increase greenhouse gases, unfairly burden the most vulnerable, incur unjustifiable costs. These are the various factors that amount to maladaptation. Reduce incentives to adapt. Okay, that's not good at all. Or limit choices available to future generations. Okay, so decision making that ignore science, wider implications or likely consequences can lead to maladaptation. Actions favoring one interest group over another laying ground for future conflict and damage. That can also end up being maladaptation. Unwise trade-offs, short versus long-term benefits, risk versus reward, where there is a moral hazard, which is a social science term we haven't strictly defined here, goes back to climate justice, disparities, and other issues. Too short versus too long consideration period. Actions that determine path dependency and lock-in, or that eliminate choices of future generations. Relocation that puts populations in even more threatening conditions. So these are various options that can end up leading to maladaptation or just unintended consequences. Here are some examples from this site here. For drought, agriculture, water scarcity, and health. So climate change obviously disrupts the hydrologic cycle, and droughts are expected to become more intense, frequent, and persistent. By 2025, 48% of the global land area will likely become dry lands. We looked at one example where between 1980 to 2015, 5 million square kilometers have been moved towards desertification. So recurring droughts forced 70% of poor Somali pastoralists into charcoal production, leading to the clearing of woodlands that accelerated desertification and increased vulnerability. Okay, charcoal is not good for greenhouse gas emissions anyways, but this is an adaptation they did for livelihoods based on what was caused by climate change, but they moved entirely in the wrong direction. Okay, agriculture, persistent climate change extremes threaten agricultural production systems. Farmers pride themselves on their adaptive capacity. I mentioned before how farmers adjust to late arrival of rain, for example, and adjust their crop calendar on year-by-year experiences. Obviously, they have to do this. Farming is really a suicidal way of making a living, but nonetheless, frequently and persist. So sorry. But these extremes arrive so frequently and persist so unpredictably that adaptation becomes a constant concern for farmers. So some Zimbabwean farmers, for example, offset climate uncertainty by increasing pesticide use. So they just started compensating for climate impacts by just putting on more pesticides. Too often beneficial insects are also eliminated, making conditions worse. Brazilians double cropping started after the introduction of climate-specific cultivars. As rain onset shifts, these practices become maladaptive. Okay. Similarly, there are examples of water scarcity. Mexico City faces water scarcity. Exploiting distant groundwater resources is a short-term solution. Actual adaptation invests in longer-term solutions such as rainwater harvesting and grey water treatment and use. Even in India, you have these tanker services in urban areas and even in rural areas, but mostly urban areas where rich people can just pay someone to bring you water to your place, but you don't care where it came from, whether it's sustainably being exploited, and so on. So this is not a good way to deal with water scarcity. It is an adaptation, but it's not a good one. Air conditioning use that I mentioned is another example of dealing with temperature increase, for example. In terms of health, antibiotics are overused, misused for both preventing and treating veterinary challenges. This maladaptation to vector-borne diseases exacerbates threats of antibiotic resistance, which has become real now. There are many resistant strains of diseases emerging. A study showed that dung from cattle treated with antibiotics emitted more methane than antibiotic-free dung. Antibiotic residues also altered dung beetles' gut microbes, and of course there is a question of groundwater being contaminated by all these maladaptations, using antibiotics to feed the cattle for various reasons, which often don't have a scientific basis even, right? So we have to be careful about maladaptation.